So, welcome back to the last lecture in the course of rapid manufacturing. In this lecture, I have just put some live case studies from the industry, and you will see how rapid manufacturing is happening today. If you want to understand, or if I have to put in a very small capsule or in a nutshell, rapid manufacturing basically is used to reduce the product development cycle time. When we talk about technology readiness level 1, 2, 3, 4, 5, 6 and 7, 8, 9. So, here it is most of the time it is called as for POC level and proof of concept and slightly advanced. So, we can say it is like alpha level. Here when it goes to here what happens is the industrial production. And 4, 5, 6 is converting this into pushing it towards the industry. Here there is some research labs or something where POC is done. Now they start working on how do we scale it up towards the production. Okay. So, when we are looking at rapid manufacturing, what we are trying to say is we are trying to shrink down this 1, 2, 3 and make it as early as possible. And also when we go to the next level, so 4, 5, 6 level, what is happening is we will also try to reduce the time here. And of course, when we talk about production, we are now talking about directly making use of the product, okay, into the industry by using some machining process to lot of versatility. So, in this way the technology readiness level or TRL level 1, 2, 3, 4, 5, 6, 7, 8, 9, this time generally takes depending upon the component for a long time. This cycle time is reduced drastically. Why? Because the ultimate aim is mass customization. Is mass customization. Okay. In order to do mass customization of products, we follow rapid manufacturing, and interestingly today the market has changed its requirements. Today we do not talk about what have you produced, we talk about what have you delivered. Okay. After all this online shopping, online food stalls coming into existence, we more talk about what is the delivery you do rather than producing. You produce, and if you do not deliver, that is not rapid manufacturing. Today we talk about a concept of mass customization and more focus towards delivery of the product to the customers. In order to achieve this, we have to go rapid manufacturing. So, I have just taken 3 case studies, one in the medical field which is exhaustively talked about today, and second thing is in automobile application, third in aerospace, and the last I would like to recap what are all the broad divisions of this course where we went through it. When we talk about medical application, we talk about Proslab ensures absolute accuracy with additive manufacturing. We will see that case study. Then when we talk about automotive application, metal 3D printing pushes the boundaries in the Moto 2 TM trademark through a different innovation. Aerospace additive manufacturing production for aerospace materials or aerospace products. Proslab ensures absolute accuracy with additive manufacturing, which is a medical application case study we are talking about. leading Australian dental laboratories, Proslab, has fully digitized the manufacturing of its cobalt chrome removable partial dentures, RPDS. The laboratory partnered with global engineering company Renesha, who is very famous for making probes, to install what is thought to be the first metal additive manufacturing machine for dental applications in Australia. Okay. This can be used for old people, this can be used for sportsmen, this can be used for artists, whatever it is. So, they have started making partially removable partial dentures. The Proslab turned to Renesha to overcome issues with human error and accuracy by incorporating a state-of-the-art additive manufacturing machine 400 metal based machine for their application. Let us see the background. Proslab is a full service dental laboratory in Canterbury, Australia. The company was founded over 30 years ago and has always maintained a keen interest in the cutting edge technology. Proslab, right? 15 years ago, Proslab became the first Australian dental laboratory to bring in CAD/CAM processes for metal frames for dentures. Okay. So, what are they doing? They are just trying to digitize the data which is available. So, where is the data available? Every customer comes and tells them. So, what do they tell? They show their teeth, they show their jaw. They just try to use the digitization techniques like whatever we have gone through in this course, reverse engineering techniques. They scan, get the point cloud data, and then they do some patchwork correction, wherein which what we studied in CAD, NURBS, all the B-spline complex surfaces they try to take, and then what they do is they store the data. Moment they store the data, they try to develop a 3D object of it. Once the 3D object is ready, now they look into what are all the manufacturing processes could be used such that they can quickly produce the output. That is what they have been doing in the past. Now, with the existing CAD data solid model, they are now pushing that solid model data into rapid prototyping machines or rapid manufacturing machines, wherein which you use powder as the starting material or liquid as a starting material, process the building block and get the part. So, earlier they used it for CAD scanning and identifying the process and quickly developing the process plan and then getting the output. Now, they have moved into additive manufacturing and they have moved into rapid manufacturing. Before working with Renesha, Proslab introduced a partially digital workflow using 3D scanning and digital tools to design dentures. This is what I was trying to say. Moment you have data with you, a solid model data, then you can start thinking what are all the process to be done and what are all the sequences to be carried out, what are all the locating points and how quickly you can get the required output. Okay. Once designed in CAD, so what is a CAD? Point cloud data to solid. The denture were printed in resin. This is after additive manufacturing coming into. They were printed in resin. Then using traditional lost wax casting were manufactured in cobalt chrome. Okay. Now, you see CAD they made through resin and they had a pattern. So, this pattern, okay, they immersed it into the wax and they manufactured a cobalt chrome output product. This traditional uncontrolled process that reduced the accuracy of the part despite careful design. Why? Because of this lost wax casting. Here we look for very high precisions, by the way, and it is a 3-dimensional object. So, along the form, if there is a deviation, the error will be very high. So, training and support were their priorities when purchasing the machines. Throughout the process, Renesha offered outstanding technical support and training to meet this requirement. We were confident that our investment, as we trusted the product for the very beginning. So they had a trust. So here what I am trying to say in front of you is not to advertise a company. We are just trying to say, please replace, if you are not comfortable, Renesha with a company which supplies a machine supplier. And this in the lab, whatever it is a research lab or a dentist hospital. Okay, a dentist hospital joining hands with lot of trust with a machine, and the machine developer gave enough of support such that whatever was the dentist imagination could get converted into realization. This trust combined with the exceptional support meant that there was not one moment during the process where we felt uncomfortable. This a company supported. So this is the typical lab environment where they work, and please do understand, it is very rare to find two human beings having a same facial and dentistry patterns. Okay. So this is the Proslab dental laboratory. You can see digitization is there, people keep working on process plan, people keep finishing the part, all these things are there. So what are the challenges did this company face? It is not a catwalk. What I discuss in the class and what I discuss in this course, as though it is the after this next step happens, after that next step happens, it is not so easy. It evolves. When the process of evolution happens, then challenges become easy to handle. A Proslab, the lost wax casting technique started with producing a CAD design of the denture, which was then printed in resin and used to make investment molds. Okay. So now you see, we made resin, from the resin you made a lost wax casting technique was used, and then what they did is they made molds. Now these molds will be filled with the final material whatever it is to get the part. The part would then be de-invested, trimmed and casted before being cut and polished. So cutting and polishing are finishing parts, finishing operations. During the process, accuracy can be reduced by dimensional change as a result of uncontrolled heating and cooling. In casting, the biggest challenge is the thermal gradient control. If we don't do the thermal gradient control properly, the product whatever you, the quality of the product whatever you get is no way good. As I told prior, grain engineering is one area where people are working hard to get uniform strength and tailor-made strength at the desired locations. So uncontrolled heating and cooling, varied varied cross section, because across your teeth dentures the cross section is not going to be uniform. See, as far as engineering applications are concerned, where you design a product and start doing, we will always make sure that design for manufacturing concept is used, we make it in such a way such that it is easily doable. But when we want to make spare parts for our body or biomimicking some products or applications, then there is a huge challenge, because it has free-form surface, and keeping sensitivity in the mind, there are places where the cross section keeps changing drastically. Free-form surface is one challenge, cross section change is the other big challenge. So by reducing the dimensional changes as a resulting uncontrolled heating and cooling, varied cross section and incomplete casting and gas porosity was a challenge for them to avoid. Though data was done by CAD and then they used investment casting method, which is very well known, they still had these two problems, because when you pour, removing the porosity is a challenge. Achieving a high level of accuracy with lost wax casting is difficult. So this means framework often need to be reworked after being sent to the dentist and fitted to the patient. So finally, when it is fitted on to the patient, there was always a grinding operation required, which always put the customer, the patient, into a mental stress. So in front of the customer, if you start grinding something, he or she feels very uncomfortable, and they have a depression that how well it is going to work. So doctors generally try to avoid rework in front of the patients, because if it is exactly fitting, the patient will also go with confidence that yes, something good has happened. Okay, it's only a mental block. The most accurate method on the market to manufacture removable partial dentures is additive manufacturing. So 15 years backstory, now they identify additive manufacturing is the possible route to get out. However, incorporating this technique involves significant change to the company's internal process and business model. If you want to move as a company towards rapid manufacturing, there has to be two important things to happen in your company. One is the mindset of every stakeholder in the company has to change. Two, there has to be initial high capital intensive investment to happen. To successfully implement the new technology, Proslab required training and support which is not universally offered by additive manufacturing system providers. So, this is the denture built plate inside Renesha. This is the machine. So, getting the scan data, they were able to make multiple products, each of varying denture size and shape, they were able to make to the highest accuracy. Here you can think of using laser as a source, you can think of using E-beam as a source. Moment you go for E-beam, you have a precise control. Laser has its own advantage and disadvantages. So, you use any one of the sources inside the machine and start using metal powders. Powder means it is not pure powder, it is an alloyed powder. Mix it and then you can start getting it. Okay. The solution was Proslab turned to a global engineering company, Renesha, to fully digitize its manufacturing process by additive manufacturing. Now it is very easy. Lost wax casting is removed. Further manufacturing processing time has shrunk down. You have all the data, hit the data inside the machine, get out with the product whatever you want. Okay. To demonstrate the accuracy of the process, Renesha manufactured sample parts at its health center care of excellence in Miskin near Crankfield, UK. Our dental production facility runs daily today. So, there was extensive data to prove that additive manufacturing was a viable if not an ideal solution. Please make a note, it need not be the ideal solution, but it can be an alternative and a viable solution. Looking into the cost. However, the raw material cost is still high when you talk about metal parts. Even today it is expensive, but however all the companies have come forward to accept third party powders. So, moment there is a third party powder available, then with the business competition available, now the prices are getting slashed down. Impressed by the quality of the sample part, Proslab purchased Renesha AM4 metal additive manufacturing system. The machine enabled the production of removal partial dentistry directly from CAD file, eliminating the additional casting step in between. So, you made resin, then from a resin you made a last wax, from a last wax you made a mold, through a mold you got the output. Now, directly you get the output. The framework was built in 40 micron layer of CE marked cobalt chrome powder and built by the laser powder bed fusion, which we have already seen, using a high power yttrium fiber laser. Okay. To ensure the transition was smooth, Renesha dedicated additive manufacturing team conducted a week-long training course with the Proslab staff. Renesha also offered ongoing support from Renesha Oceania in the Mulgrane, Victoria. So, finally, they could get the required output. The Australian team remained in contact with Proslab to answer any question. The training and the support was our priority. That is what I said. Any modification has to happen in an industry. You need two important things. One is skilling the manpower. So, it has to be a manpower wherein which they are ready to learn new things and they should be agile to accept the technology. Today technology is changing very fast, beyond your imagination. What earlier we talked about a generation, my father was a generation, right. Today when I say generation is 10 years, and when I talk to my undergrad students here, they say generation is 4 years. My son who is in school talks about generation of 1 year. The time scales have shrunk down. So, you should be ready to accept technology and you should be agile to keep moving in developing it. Throughout the process, Reneshan offered outstanding technical support and training to meet the requirements. So, please, I repeat once again, Reneshan, you can replace it by any company. Company offered, whoever is the supplier. See, the new development can happen when all the team members who are working not within the factory, but outside the factory also should work on a common cause. Then we were confident in our investment as we trusted the product from a very beginning. This trust combined with the exceptional support meant that there was not one moment during the process where we felt uncomfortable. So, these are the dentures which were built. So, it was very good. So, these are the dentures, these are the supporting material. These are the original material. Original material means final product. Okay. The result is now able to produce the most accurate framework possible. Direct printing from a CAD file means we have reduced the number of in-house remakes due to error by 100%. So, you have a proper data, most probably the first part what you produce is the final part, and we have stopped doing rework on it. If any error were to be occurred, we quickly be able to identify the source and amend in it. So, nowadays you have very good simulation softwares. These simulation softwares, what they do is they try to make sure before they try to show layer by layer how is it building, when the laser moves how is it building, is there any porosity coming, is there any delamination happening between layers, whether the melt powder is perfect. So, you should have a uniform homogeneous heating. Because of the improvement in the accuracy that AM400 offered, Proslab can now ensure each framework is a perfect fit to the patient, which is a big breakthrough. See, the online business, whatever is happening today, has become so much, it has changed the perspective of a customer. Earlier, if I say my son that I have booked a cycle for you, he will be ready waiting for the cycle even for a month. Today, the technology has gone so much, if I say I have booked for the cycle, next he asks when is my delivery. So, because of so many things happening, so the technology development, we are able to produce what a customer wants. The first part is the best part, so the delivery time is reduced drastically. And again here, by using all these RM techniques, additive manufacturing or rapid manufacturing techniques, these examples what I present here in this case study is a single part a product. If you wanted to have multiple parts getting assembled and then you take a product, even now it is a challenge. So, the way out of it when we talk about rapid manufacturing is they are trying to make the product or the part structure more complex and reduce the number of parts, so that what you make is perfect and the delivery is on time. This helps to improve the protested service, or I would say dentist service and the reputation, benefits patients by offering improved fit and removes any delay that may occur if the framework is not right first time. Result, there is a major advantage. The framework we produced are now guaranteed to fit every time, which means we have been able to rise turnover. Partial denture is half the time continued The difference in fitting has been amazing. We are now gaining more customers for it as we can ensure that the customers will receive the best possible fit dentures. By cutting down the casting step, we can now produce removable partial dentures in half of the time. We save an entire day of processing, which means that we have been able to upskill our casting staff into manufacturing role. So, our process is reduced, the production time is increased. In the production time, it has to be a delivery time has reduced a lot, and you are able to produce and deliver sound products. So, this is during the process of melting. So, you can see laser is hitting. When the laser interacts with material, the powder material. So, when light hits at a material, or I would material, and the light is hitting, you can have reflection, transmission and absorption, right? Absorption. So, when the light reflects, it is this spark you see that outside. When it absorbs, it heats and melts, and very rarely it transmits. So, here we use these two phenomena in a large extent and we get the required output. So, polished RPD on a stone mold. The next one is metal 3D printing pushes the boundaries in Moto2-TM through defined innovation. Okay. In the higher octane in the world of MotoGP TM motorcycle racing, technicians' enhancement have been a big impact. So, that means to say, earlier there were more number of parts, and when there are more number of parts, the assembly was always a challenge. When you run at very high speeds in this racing bikes, very high speeds, these even a small stone gives a big jerk, and these get unassembled. So, now what has happened is they have stopped using large number of parts, and they have made the part geometry complex, integrated all the assembly into a single part itself, and see how best they can do. For example, if there is a ring and if there are rods which are attached to it for fastening, now this rod along with the ring is built up right there. So, number of processes are reduced and the parts are getting integrated into one part, the part geometry has become complex. So, this will try, and you can also selectively strengthen the part wherever you identify there is a failure zone. Here alone you can have more material compared to rest of the pipe, that is you decide. The race winning Moto2 team Transformers is using cutting edge additive manufacturing technique in an unconventional front suspension system to gain a significant competitive advantage. Okay. So, they are started working, the weight is reduced, the suspension quality has enhanced, so the rider is given more comfort. So, the motorcycle riding with the MotoGP World Championship are special. The general public cannot buy them and they cannot be used on a public road. As prototype race biking, they are custom built to outdo their rivals and maximize performance on the tracks. Moto2, the second of the third MotoGP class, was created in 2010. Its official engine is 600 cc. Typically, what in Indian conditions, earlier we used to talk 100 cc as the high power. Now we have also moved to 100, 125, 150, 200. It has come. Okay. So, but what engines are used in this particular racing bike is 600 cc with 4-stroke production engine currently supplied by Honda. Okay. The French Moto2 team Transformers, based in southwest France, is revolutionizing front suspension design in order to stay ahead of the pack, that means to say of their competitors. Transformers is led by former 250cc world championship rider Christiana, and the team unconventional suspension system was inspired by a seminal work of a legendary French motorbike designer Claudier and Four. Christiana, former friend and mentor Foyer, recognized the gain to be made from isolating the front suspension from steering forces. Suspension will be independent, steering forces is the front frame is independent. So, this gives them a more flexibility or applies less force for steering, be more sensitive towards steering. Okay. Resolving issues of brake dive and design enabled later braking into the corner, faster acceleration out were put as the objective functions, and this was done. The weight reduction that metal 3D printing have achieved for us in our wishbone component has enabled us to bypass traditional weight transfer phenomena and problems associating with brake die. More than that, it allowed us to design a part that is not only lighter but far more rigid at the same time. So, weight of the vehicle goes down, efficiency goes high, a number of components attached to the steering has been reduced. So, if you want to do this trial testing, you have to do many things, and in the conventional way it takes a hell a lot of time. By using this rapid manufacturing techniques, they could iteratively change and get the best fellow out of it. Instead of the more traditional telescopic front fork suspension, the Transformers motorcycle employed a rigid front fork suspension system separated from the chassis using two wishbones. To further advance the development of the innovative design, Transformers approached i3D Concept, a world-class expert in metal additive design and manufacturing technique. So, they made good techniques, they did some analysis, software simulation analysis, and they felt that yes, this is going to be the trend setter. Then immediately what they did was, let's make few prototypes and see. So, they approached an additive manufacturing company. Using Renesha AM250 additive manufacturing system, i3D Concept worked in partnership with the Transformer team to optimize the design of its upper wishbone component, one of two attaching the front fork to the chassis and critical to the bike's steering. The challenges when faced by them is, it is not as challenging as the first case what we studied. Biomedical is a very challenging case, but here you conceptualize, you imagine, and engineering design to a large extent is not, it's not so much of free form, and the cross section area does not vary so drastically like in the dentures case. In the development of new components in motor to bike design, achieving a weight reduction is a priority, because here that is what is a priority. So, in particular, reducing the unsprung mass of the bike is a key consideration. Okay, jumping of the mass. The lower the unsprung mass, the better is the suspension in the terms of vibration management and the responsiveness to both braking and acceleration. Unsprung mass, vibration. Of equal importance, it is the speed with which the design of a new component can be modified and how long it takes to remanufacture. Achieving perfection in a highly competitive environment demands fast, accurate component iteration. In a high reliability environment, mechanical strength is a further prime consideration. The Transformer's wishbone component needs to be assured best possible rigidity while handling significant levels of dynamic steering forces. To improve overall motorcycle performance, reducing the weight of all components located behind the shock absorber is absolutely vital. Failure to optimize components' weight can have an adverse effect on vibration, braking, acceleration. So, weight reduction is really a high priority. Okay. So, all these things were done. So, this was the original 12-part steel frame. You see that 1, 2, 3, 4, I told you, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have other sides also parts. Now, you see this is, it has 12 parts, cutting, welding, and you see it is very complex. Making a fixture for welding, okay, is a challenge. Now, you see the entire thing is done by a 3D part as one part, you see it has come, and now this has more strength, less weight, okay, or I would put stiffness, and this gives a better control over the objectives whatever we want. So, originally wishbone component was hand fabricated in steel with the assembly comprising of 12 separate machined and welded parts. So, now it is made of a single part. Okay. It is made through AM250 machine. Initially, prototype is in stainless steel and finally manufactured a lightweight part with a titanium, because titanium is much lighter, the density of titanium is lighter. Key to a new 3D component design was an iterative process of topological optimization, whereby the wishbone layout was successfully rationalized in software within tight space constraints to understand a set of predefined front fork loading conditions. Once the final component was designed and validated using a digital CAD software, when I say CAD software, it does not mean drawing alone. CAD means it is including of drawing, simulation, and they also try to do optimization. Okay. Today CAD means it is not drafting, it is design, wherein which we have simulation, we have optimization also done in terms of shape, material, whatever it is, right. So, once the final component design was validated using a digital CAD software, the built preparation file was separated offline prior to export to the additive manufacturing system. Within the CAD software, i3D concept was able to assess whether the parameters were efficiently predetermined or whether they require tweaking to match the specific metal powder characteristics and complex target geometry of the transformer's visor. Importantly, using AM250 dedicated optical control system software, i3D concept was able to very accurately control laser steering with a help to enhance precision and also control the surface finish. So, this is a CAD developed of additive manufacturing of using titanium, and here is a part, this is the CAD. Look at it, how have you reduced? This is rapid manufacturing. You have reduced the cycle time in terms of manufacturing also. Result, by taking an additive manufacturing approach, motor 2 bike design transformer succeeded in drastically reducing the weight of its critical wishbone front suspension components by a factor of 40%. Comparing the one piece titanium component with the original welded steel component, a weight saving of 600 grams was achieved. It is a huge reduction. So, you get more speed, you can win the racing bike. Okay. Metal 3D printing has been also proved transformed with much finer control over component tolerances and the flexibility to a very quick iteration wishbone geometries to match the specific chassis and kinematic requirement. The weight reduction that 3D printing has achieved for us in our wishbone component has enabled us to bypass traditional weight transfer phenomena and problem associated with brake drive. So, this is what it is, a CAD model has been developed, it has been manufactured. So, then what you can do is when the part is get produced, you have the other powder, free powder particles. This is how the free powder particles are removed. These are the supporting structures, this is the final part. Okay. And this is when it is fixed, when it is put on application, this is how it looks like. So, part of one piece titanium which is done, this is the bike which they used it for winning. So, I have used this and on Renesha website it is there, they have put many more applications, and what I would suggest all the students is to go through this website, learn more case studies which is available there. I have picked all the case studies from them, and this is what the copyright which is given, and they approve it and agree it that we can use the case study for educational purposes. So, for aerospace, BAE system, regional aircraft providers support and engineering services for its in-service fleet of some 500 commercial aircraft worldwide. They have, BAE is a system. As part of the original spare support for the BAE 146 regional airline, the company needed to replace a small pipe which forms part of a cabin window and stop the windows misfitting up. So, the part known as breather pipe had originally been made via injection molding, but the tooling has become damaged and the replacement tooling was expected to take months to produce and the cost was so much. So, this is a pipe which has to be produced. This is required for the OE, original component, which gets into the part fabrication and also to the spares market. And all of a sudden one fine day the injection molding die got damaged. So, it is important to produce the part rapidly, as without this small but a critical part the plane could not be grounded. So, BAE system regional aircraft turned to a 3T RPD and additive manufacturing for a solution. So, this is the CAD model of BAE system breather pipe showing smooth angle of turn. Aircraft team Prestwick realized that 3D manufacturing can provide an elegant solution to this problem. They designed the replacement breather pipe, and these were prototyped by their colleagues at BAE System Military Air and Information. Then regional aircraft worker with 3T to develop the product for the production of 3T to build batches of parts. The 3T used the CAD drawing from the customer and produced a number of example parts. The quality assured inspection highlighted potential for improvement prior to the ongoing production. The original pipe had a smaller diameter with a sharp bend. So, that could be reduced because the conventional manufacturing was putting a restriction. Both these features caused problem, as it made the removal of the loose powder difficult, and loose powder left in the pipe restricted the airflow, thus making the part unreliable. So, the CAD was modified to widen the pipe diameter and smoothen the line of the pipe. So, the radius of the bend was less acute and more rounded. So, they could get the part done to their requirement. After working with 3T, the part are now in stock at BAE System Regional Aircraft Spares Warehouse and are being used by its customer for use on the in-service aircrafts. The projected timeline for producing the part using injection molding was 6 months, yet using additive manufacturing this has reduced to 4 weeks. So, this is what is rapid manufacturing, and they were also able to improve the quality of the product. Having achieved the first breakthrough on the DAE 146 window breather pipes, we are now looking at a range of other 3D printing opportunity to provide replacement parts across several different commercial aircraft types. The technology offered a potential solution for aircraft parts which are prone to obsolescence, where tooling is unavailable for quick turnaround and also for small batch production. So, DAE finished breather pipe, this is what it is, and it is made out of metal. So, to recapitulate what we covered in this course, the course flew in this fashion. Introduction to rapid manufacturing was done, and I gave you an example of a year. So, I taught you how to do rapid manufacturing, rapid tooling. I talked to you about indirect tooling also. Then we talked about product design processes, design for modularity. In that, design for manufacturing, assembly and design for modularity were discussed. Then we would also saw the advantage of subtractive process versus additive process comparison. Then we entered into rapid manufacturing process. First we saw powder polymerization process, where we saw both liquid as a starting material, we saw that. Then we saw powder based process, wherein which most predominant one is SLS, SLM, okay. We saw that on top of other processes. Extrusion, we saw FDM process and other liquid based processes we saw. Then sheet stacked process, basically a loam process we saw here. Then 3D printing processes, wherein which we saw how glue could be used, glue or additives could be used for joining powder parts to produce the output. And finally, we saw how to use laser as a heat source or E-beam as a heat source to get the output. In between, we also had in this course lab demonstration for reverse engineering, for 3D printing. Then we also talked about post-processing concern. We saw about rapid manufacturing materials which are there. Costing for rapid manufacturing was also dealt in this course. So, this too is very important. Costing is something which people always ask. One is capital cost, another one is recurring cost. So, we discussed about that. So, rapid product development, Computer-aided design we saw, wherein which we talked about 2D, 3D, solid, surface, boundary representation, all those things. Manufacturing of additive processes. Why is this important in additive manufacturing? We saw that. Then plant design and simulation of additive processes we saw. And finally, today we saw some case studies, one in biomedical and auto, and we also saw aero. So, these are the three case studies we saw. When we see these case studies, I am sure you will appreciate the rapid manufacturing is going to be the future. Thank you very much.